Hello. In this video, I will demonstrate how to solve the single period inventory model using the Microsoft Excel data tables. So let's get started. Consider a problem that deals with a vendor and sells fireworks once a year around 4th of July. Fireworks come in packages and sell according to a uniform distribution with a low of 10,000 units and a high of 40,000. Each package costs $9 to purchase and sells for $12. Extra packages are sold at a discount price after July 4th at $4. The question is, how many packages should the vendor order? I am going to first solve this problem using the analytical way and then demonstrate how to solve the problem using data tables. So for the analytical table, we need to calculate the probability of demand less than equal to the optimum order quantity. Remember, this is a single period model. Okay, our purchase cost is $9 per package. Sale price is $12. Discount price is $4. Demand is distributed at uniform between 10,000 and 40,000. So first we have to calculate what is called the potential loss per unit for overestimating the demand, or CO. That in this case is going to be the purchase price minus the discount price. This is for ordering too many units. Next, we have to calculate what is called a potential loss per unit for underestimating the demand, or C of U. In this case, the C of U is equal to the sale price minus the purchase price, for a profit of $3 per unit. Next, we will calculate the P of demand less than equal to Q star, which by definition is CU divided by CU plus CO. In this case, this is going to be 0.375. We now use this probability in order to calculate the optimum order quantity. In this case, because the demand is distributed as uniform between 10,000 and 40,000, the optimum order quantity is going to be the low value of the probability distribution, which is 10,000, plus the probability, which is 0.375, multiplied to the range, which is 40,000 minus 10,000, and this turns out to be equal to 21,250 units. In other words, the vendor, in order to optimize or maximize his profits per period, should order 21,250 units. So this approach is called the analytical approach to the single period inventory model. I will now demonstrate how to solve the same problem, assuming that we didn't have this equation or the formula for this inventory problem, and we would want to resort to computer simulation. The data table is the best way to use this to solve this problem using computer simulation. So let's take a look at that. Okay, here is a spreadsheet that I'm going to use to demonstrate how to solve the same problem, single period inventory model, in this case using simulation via the Microsoft Excel data table command. Let's look at our parameters first. So again, we have the purchase cost, which is $1 per unit for $9. We have the sale price, which is $12. We have the discount price, which is $4. This is the number that we want to find, the optimum order quantity. For now, I'll just enter a number such as 30,000 to see what happens after we complete the simulation. For the demand, This equation for the demand, of course, is the uniform distribution, which is the low end plus the probability multiplied to the range, which is 40,000 minus 10,000. And now we have to determine the equation for the profit. So equation for the profit is going to be dependent of if the demand is greater than order quantity or is less than order quantity. If demand is greater than order quantity, this is just the name for the cell, is Q star, which is the order quantity, multiplied to the profit, which is B4 minus B3, B4 minus B3, sale price minus purchase price. However, if the demand is less than the optimum order quantity, we will have some leftover. So it will be the demand multiplied to the profit, which is the same as before, B4 minus B3, plus the remainder, which is Q star minus demand, or optimum order quantity minus demand, multiplied to the discount price, which is B5 right here, the discount price, minus the purchase cost, which is B3 or $9. So now we are ready to use the data table and simulate this equation for a number of trials. In this case, I have already entered the number of trials as 1,000. I'm going to use 1,000 different trials to determine the profit for different order quantities, or different demand values that come from the probability uniform probability distribution. So to use the data table, we're going to have a number of trials, which I have put here, and then we will enter the value of the parameter that you want to generate at different probabilities. In this cell, we are going to put the address of the parameter that we are using the probability distribution to generate. And then here is our metric, which is profit. So we'll put the equation, the cell address for profit here. Okay. And I will later show how to calculate the demand less than the optimum order quantity. Now, in order to use the data table, we have to highlight this entire range all the way to 1,000. And then we will go to the data command. Then we go to what if analysis. We select the data table. In data table, because we are using columns, we have to put in a column cell input. Again, because this is just a random trial, we are not using any values to enter into the column input. I just put a hypothetical address here, a random address. Let's put D1, cell D1 in there. And then we will click OK. And notice what happens is that the data table command generates a whole bunch of demand values probabilistically for different random numbers, and for each one it calculates the total profit. Now what we would like to do is to find out if in fact we have used the optimum order quantity in order to come up with the best profit. For that, I will have to calculate the average profit. So in this case, my average profit will be located here. So this cell is going to be equal to the average of this cell all the way down to so our average profit is going to be 36,295. The question is, we don't know if this in fact is the maximum profit we can obtain by ordering 30,000 units. So let's take a look at what happens if we order 35,000 units at a time. Well, the average profit drops to 22,500. So obviously we're going in the wrong direction. Let's suppose we order 15,000 units at a time. Well, the profit goes up, but is that better than before? Let's go to 20,000 units. We know the optimum order quantity is about 21,000. So you can see that by varying the order quantity in this cell, we can actually go ahead and see what happens to the average profit. And eventually, if I put in the 21 to 50, which is my optimum order quantity, that is the highest average profit that I will get. We now want to determine how often the demand is going to be less than or equal to our optimum order quantity. So that will give us a percentage of number of time that we are short. So for that, I'm going to first count the number of times that demand is less than or equal to Q star. So if my demand, which is B, 6, less than or equal to Q star, I'll let this value be 1, otherwise I'll make it 0, and let's see what happens. Notice that in this case, for this trial, demand is 24,000 and optimum order quantity was 21, 20 to 50, so obviously that's a 0, and I'm just going to copy this formula all the way to trial number 1000. Next, I will count the number of ones that have occurred here. For that, we will go to this cell, and I had already entered the formula. We say count if D11 to D1010, which is almost 1,000 rows, if the value is 1, and that gives us the count. And in this case, we get 383. So notice that in 1,000 trials, 383 times we have demand less than or equal to order quantity. The probability of that is 383 divided by 1000, which is about 0.38. Well, notice that this value of 0.38 is approximately equal to the number that we have found here. Remember, these are random trials, so each time they change, but they're approximately the same. For example, if I just put a number here and change that number, see what happens, it goes to 386. So this is basically how we solve the single period inventory model using the data table to simulate 1,000 trials and then compare different random demand values from a uniform probability distribution to an order quantity, and we can vary the order quantity to see what happens to the average profit, and by trial and error we can determine the optimum order quantity for the best profit.